Very much. Thank you for the feedback, Mahmoud, in the chat. So it's just past 1 o'clock, in fact, but I know that many of us had a power cut at 1 exactly. So maybe some people are still trying to get in. So I'll just chatter for a couple of minutes to introduce you, Dr. Habre. I think the important thing is to make sure that all the participants have joined us by the time you start speaking. So I just would love to welcome everybody once again to our School of Arts and Sciences research seminars. Whatever kind of week you've had, and I'm sure it's been very eventful and very special, I hope you can kick back for the next hour, forget about all the nonsense that's going on around you, and let's engage in an amazing piece of intellectual research that our own colleague, Dr. Habre, who's an associate professor in mathematics, is going to present to us. We are going to have more of these research seminars. We're trying to keep them happening in the summer and across the year. I don't think they should only happen during term time. And most recently, I was speaking to our colleague from the English department, Dr. Luma Bala, and we had this idea that we should do research seminars that are not just typically about actual research. And so we are hoping to advertise very soon a creative research seminar. And we hope that many of you who are here today, who are clearly interested in mathematics and in Dr. Habre's work, I hope that you will take the leap and come and join us when we do the more creative and artistic research seminars, because we're hoping to prepare something quite unique as well. So it's 1:04 now. So without further ado, I'm going to hand over to Dr. Samir Habre to enthrall us with his research on mathematics. And I will say, just in brackets, I know you're here in your capacity as researcher today, but you are actually one of the most inspirational teachers as well of mathematics. And I will tell the audience that when I advertised to my family that I was coming to Lebanon to take up a job at LAU, my brother-in-law, who did his computer science degree at LAU a while ago, let's not say a long time ago, because that doesn't look very good for you, Dr. Habre, a little while ago, told me, oh my God, the best teacher ever is at LAU. And he asked me to find you, and I did find you, and I did tell you that he's still very fond of you many years later on. So on behalf of all the students you've ever taught and inspired, I want to thank you, and I'm really handing over to you now for your talk.
Thank you very much, Dr. Znainati, for this lovely introduction, and thank you everybody for joining me today. When Dr. Znainati told me, asked me, or we were discussing, the research seminar series, and she mentioned that maybe I could give a talk. I was a bit hesitant at the beginning because, this is mathematics, but then I decided I could give something about my research and the teaching of mathematics, something that is not very technical, something that I hope everybody will be able to follow as I'm giving presentation today. So the how can I'm not being able to move my let's see, my PowerPoint, just a second. Okay, let me see. Can I do it now? Yes. So here is the outline of my presentation. The focus of my presentation is going to be on a subfield of mathematics called differential equations. So I will tell you why differential equations. And then I will talk a little bit about an educational theory of the realistic mathematics education, RME, followed by something called inquiry-oriented differential equations, or IODE. And then I'll share with you a classroom experiment I did at LAU, some of the results of the research I have done with this classroom at LAU. So why differential equations? Differential equations, so now I want to try to make this a little bit, I want to make sure that the people who are not mathematicians in this room will understand what I'm talking about. So differential equations is an applied field of mathematics. It is used in physics, it is used in chemistry, it is used in biology, it is used in economics, even in some of the social sciences as well. Because it is such an applied field, modeling is therefore very important. Can you not see my PowerPoint?
I can only see you, Dr. Habre.
Oh, just a second. Why is that? So share screen. How about now?
Yes, we can see it now.
All right. So I was saying, why differential equations? Well, because it is an applied field in mathematics. It is used in physics, it is used in chemistry, in biology, in economics, and even in some social sciences as well. Therefore, because it is applied, modeling is very important. Now, what is modeling? Modeling is the process of rewriting a real-life problem into mathematical terms, using mathematical terms. Now, a little bit of mathematics here. In differential equations, the basis for modeling is the concept of rate of change. Rate of change measures the rate at which a quantity increases or decreases. So this is something that we're going to be talking about frequently in this talk, the rate of change. Now, to show to you how important is the field of differential equations to real-life applications, I want to share with you information about a journal called the CODE journal. CODE stands for the Community of Ordinary Differential Equations Educators. Now, I am a board member, a member of the editorial board of the journal, and I was also the guest editor of 2 recent special issues of this journal. In 2019, the theme of the special issue was linking differential equations to social justice and environmental concerns. So the title by itself tells you how important differential equations is to real life situations. For instance, in that issue, there were articles about climate change, articles about the prevention of malaria, the spread and prevention of malaria in Central Africa. There were a couple of problems that we call SIR models. S is susceptible, I is infected, R is recovered. This is very much in tune with what's going on now with COVID. There was even an article modeling gossip. Now, in 2021, just now, actually, the other special issue is up now on the website of this journal, and the theme is engaging learner differential equations for today's world. And some of the articles there are about the Ebola epidemic, whale population in some bay in the United States, the dynamics of 3 species fish population, and also an article about, one of the articles is about the refugee crisis in Europe. So you can see how important differential equations is to many fields, including the social sciences. To put these things into perspective for those who are not mathematicians, I want to give you a very simple example of a modeling problem. Suppose that P represents a population of a certain town. This population is a function of time, so we represent it by P of T. That population changes with respect to time. It either increases or decreases. And there is a rate at which this population increases or decreases. In mathematics, we represent this by P prime of T or dP by dt. So you're going to see this a few times in this presentation. Oops, excuse me. What happened? What do you see? Oh, okay. So for instance, an example would be P prime of T of a differential equation is 0.3 times P of T. What that means is that the rate of change, that P prime of T, depends on the population itself, on the size of the population, which is obvious, and it is 0.3 times that population. So the bigger the population, the faster is the rate of increase. Now, in the second equation, it is negative 0.3 times P of T, which means you don't have an increase, you have a decrease in the population. Now, what do we want to do with these equations? We want to solve them. That is, we want to find a function P of T that will tell us what the population is at any time. So here is something graphical, visual about the population. You can see the graph, right?
Yes.
Okay. So in this graph here, there are three curves, red, green, and blue. They all represent populations. And of course, the difference is that, just to make things clear, the horizontal axis is the time axis, the vertical is the population. So this is telling us how the population is changing as time increases. The difference between the three is where does the population start? What is the size of the initial population? So those are three models, okay, of population increase depending on where what the initial population is. Now, if I may ask the people who are not mathematicians in this room, if you look at one of these graphs, let's say the blue graph, how do you read it? And do you see anything that is not very realistic about it? If anybody can share. Haidar, can you unmute people? Would anybody would like to say anything about any of these graphs? Okay, maybe not.
Okay. It is increasing.
Okay.
Steeply increasing.
All right. It is increasing and increasing without any bounds. It seems to be increasing indefinitely. And that's an issue because populations should not be increasing without any bounds, obviously. A more realistic model would be something like this. In this model, let me explain it to you. In this population model, if you look at the red graph, in this graph, the population is increasing initially at a low rate, then a fast rate, and then it reaches some sort of an equilibrium. There is this threshold where the curve flattens. You've heard this terminology this year and last year a lot about the virus. So the curve is flattening here, which means the population is reaching a certain equilibrium. If you look at the green graph up there, it is actually a decreasing graph until it reaches that equilibrium. Well, what this is saying is that there is this threshold of 10, whatever that 10 means. It could be 10 million people or 10,000 people, where if you start above that population, the population will decrease until it reaches that equilibrium. If you start below, it will increase, but it will not go beyond that equilibrium. Why did I give you these examples? Well, because this is the kind of thing I do in my classes. When I start discussing differential equations in my class, I start by looking at these real-life examples. Another real-life example I look at in my class when I start differential equations is a model of two species interacting with each other, such as rabbits and foxes. So if you think about it, you have rabbits and foxes in some environment. They are interacting with each other. In the absence of foxes, the rabbit population will increase, but in the presence of foxes, the rabbit population will have to decrease because the foxes will survive by eating the rabbits. Now, if there were no rabbits, assuming there are no other means for the foxes to survive, the fox population is going to decrease, but in the presence of rabbits, the fox population increase. So again, we model this graphically by a graph such as this one here. Again, I'm showing you three graphs, but they all mean the same thing. Here in this graph, the horizontal population represents rabbits. The vertical population represents foxes. And we move on these curves counterclockwise. Well, if you try to understand this curve, it says that, well, let me move on, I don't know, let's say this green curve here. As you move to the right on this green curve, starting at that point where I have my arrow, because you're moving to the right on this curve, it means the rabbits are increasing, moving to the right, increasing. Moving up, the foxes are increasing as well. So both populations are increasing. Until you reach a point here where your motion is now upwards, but to the left, to mean that the rabbits are now decreasing. Why are they decreasing? Obviously, because now there are so many foxes that they will cause the rabbit population to decrease. So the rabbit population starts decreasing, but at the same time, there is enough rabbits for the fox to increase. So they keep on increasing until you reach a certain point here where the number of rabbits is too low for the foxes to increase in population. So the foxes start to decrease in population. So this is when the curve starts going down. The foxes decrease in population. It's still going to the left, so the rabbits are still decreasing, but the motion to the left is very little. So the decrease in the rabbit population is slow until you reach back to this point here, down here, where now the number of foxes is too small, the rabbits can increase again. And so, you know, you have that cycle of increase, decrease of the two populations, that cycle of life that we talk about. Obviously, if there were no human intervention, maybe the cycle of life will be the same, but sometimes people go hunting, they affect the population of rabbits or of foxes. This causes disturbance in that cycle of life. So as I was saying, this is what I do in my classes, because really the challenge in a classroom is not what you teach, is basically what the students are learning. So here is a comic I wanted to share with you. I taught Stripe how to whistle. I don't hear him whistling. I said, I taught him, I didn't say he learned it. So if I teach something, it doesn't really mean that the student has learned. So the underlying theory behind these examples is learning by doing. This is a challenge that we all face. We think we have given a beautiful explanation to our students, only to find out later that, you know, they have not really learned it. So what I do is I adopt a learning approach that I start by exploring examples, real life examples. We discuss the examples, the meaning of these examples of these models visually, if possible, and then we relate them to formal mathematics. This is basically part of what we call realistic mathematics education. This is an interplay between a real-world situation and the world of mathematics. The realistic mathematics education theory was developed in 1973, and basically it says mathematics should be primarily a human activity. It should be an activity of discovery, and it rejects the predominant idea of mathematics as a ready-made system to be presented and memorized by students. So when you want to do or you want to offer a class using the theory of realistic mathematics education, you have to design your curriculum. And there are three principles to design a curriculum using RME. The first principle is called reinvention through progressive mathematization. Now, this principle is accomplished by designing instructional activities based on realistic situations. Then the second principle is didactical phenomenology. This is the study of the relationship between the phenomena that the mathematical concept represents and the concept itself. For instance, rate of change and derivative. And finally, the third principle, what you need to do is you need to bridge the gap between informal knowledge and formal mathematics. Because what we are doing was very informal in these examples. I need to somehow put it all into a formal way of doing it. Moving on to the idea of inquiry-oriented differential equations. Now, inquiry-oriented differential equations is a curriculum which is based on the RME principles. This curriculum was developed by a team of 4 researchers in the United States, based on a grant by the National Science Foundations. And the curriculum is, as is the case with the RME, is based on some instructional designs. There are 4 principles for this curriculum. The first principle is you want to generate students' way of reasoning. This is highlighting the centrality of the roles of the students' mathematical reasoning in the development of a mathematical concept. And then it goes on to building on student contributions. The student is a very important element in this design here of the curriculum. Teachers want to ensure that the learners come to regard the knowledge they have acquired as their own private knowledge for which they feel they are responsible for, and this is very important. And then the third principle is developing a shared understanding. Students each is contributing in a way, but then the teacher will need to develop some kind of a common understanding among all the students. So he is a broker between the students. But then the final stage is connecting to the standard mathematical language. There is a standard mathematical language that the students need to learn, and the teacher will be, again, a broker in this case between the knowledge that the students have shared with the more specific mathematical community. So this curriculum, this IODE curriculum, does not adopt a textbook. The teacher and there are units provided to the teacher and units provided to the students. They were developed all by this team of 4 mathematics education researchers. By the way, the team of 4 people, they were not all mathematics education researchers. They were mathematicians and mathematics education researchers as well. So the units are designed in accordance with the instructional design of RME. It is intended primarily to foster student reinvention of mathematical concepts. There is a sequence of tasks in these units that build on student concepts of reasoning as the starting point, and then more and more complex and formal reasoning develops as you go on with the tasks, hence guiding the students to reinvent a certain process. Of course, there is a website associated with this curriculum. It provides all the resources necessary for teaching the course, be it through the units or through technological resources. What is a typical classroom environment? What does it look like in an IODE class? We divide the class into groups. We provide the students with whiteboards, markers, erasers. For every unit we teach, students are provided with material, and they are asked to be engaged in their own groups on specific tasks. During that time, the teacher walks around exploring student strategies, sometimes answering questions. This is followed by an all-class discussion, and then sometimes groups are asked to present their work. Finally, the teacher introduces language and notation when appropriate to formalize the students' ideas and contributions. So let me show you how the classroom environment looks like. Remember this first example we looked at, the dp by dt equals to 0.3 times p. And we said that this is not a very realistic model. Now, in one of the units in this IODE curriculum, this particular topic is actually discussed. So let me share with you a video showing a classroom in action. Just a second. Share. Okay. So you can see the video. You can see a screen now.
Unlimited resources, one species,
yes.
Production. So unlimited resources is really unrealistic. It's really not a feasible way to think about modeling population growth unless you're sort of looking at bacteria in a laboratory cell over short periods of time. Then it kind of makes sense. But in real life, there are going to be limited resources. And so the first question is that we have GPT is 3.3. And then here we also have it. If I cover up this other part here, so that 0.3p for the rate of change is still here, but now there's this extra term. And so I want you to think about how this particular change, this change from here to here, accounts for the fact that the resources are really limited.
So this video is of a classroom by Chris Rasmussen. Chris is the lead developer of the IODE curriculum. What Chris was telling his students to do, remember we talked about this dp by dt equals 0.3 times p, and we said this is not very realistic. So he said, well, because of unlimited resources, this is not very realistic. Then he asked them to look at a new equation. I don't know if you can see it quite well. This new equation, he's asking them to analyze the new equation, why this new equation actually takes into account the limited resources for the population to increase. So he wants the students to engage in a discussion among themselves to look at the difference between that equation 0.3 times p and the new equation 0.3 times p times a new quantity, why this new quantity actually makes the resources limited. Why does it imply that there are no unlimited resources here? And then I want to show you now how, you know, how the students are working on this. So this is a group of students working, they are in action, working on a whiteboard, discussing that equation. So you can see the students discussing among themselves, trying things out. Chris is with them, the instructor, you know, interfering when needs be.
Because after 10 it's going the other way, but it's not after 0, it's going the
So you saw the students in action, you saw how the instructor was, you know, moving around. I want you to look at that particular graph here, the slash field, what we call slash field. And I want to take you back to, oops. I want to take you back to my presentation. Oops, what happened here? Excuse me. Oops, okay. So that figure I showed you at the end is very much like the figure we started with in the presentation today, when I talked about the limited resources, population growth. Sometimes the population increases until it reaches a threshold, or else it decreases if it is beyond that threshold. So you saw in the video how the students actually themselves came up with this figure. So they created the concept itself themselves. I myself participated in an IODE workshop back in 2017, I think, the summer of 2017. It was a workshop in the United States funded by the NSF, but I was funded by LAU, the Faculty Development Fund at the time. Unfortunately, we don't have funds anymore to go on these trips, but I was lucky enough to be supported to attend this IODE workshop. And I came back and I implemented that IODE curriculum in spring of 2018. I was lucky enough, I would say, that the department supported me in experimenting with this curriculum. The dean's office supported me at the time also with that experiment, because I had to restrict the enrollment in my class to few students. I couldn't have a class of 40 to 45 students. I needed some material. So what I did is I was able to experiment in a classroom of 25 students. We needed to find a classroom, by the way, where I had these desks so that I can group the students into groups. So we found one in the Fine Arts building, the Safadi Fine Arts building. It was very small. I couldn't really videotape myself over there. It was a very small classroom, but we managed. We bought whiteboards for the students. I grouped them into 7 groups. They were mostly engineers, of course, because the class is required by engineers. There was 1 math student and 1 economics. And as is the case with every inquiry-oriented environment, I would be walking around the students, discussing with them. They would go on to the board and tell me what they were doing, etc. I took notes, I did questionnaires, I did surveys, I also collected homework, collected exams, and I tried to analyze basically what they did, how they improved, what was their learning like in the classroom. So I wanted to share with you a couple of observations I made. They were all published in a research article. This is one of the results one of the observations I made. So in one of the very first units in this curriculum, we give the students systems of representing species like the foxes and rabbits. But what I gave them was, or what the curriculum gives them is these 2 models here, these 2 systems. X is some population, Y is another population, and they are interacting with each other. Now we tell them that one of them is a model for cooperating species, such as bees and flowers. And another one, this one, is for competing species, such as, I don't know, lions and pumas. They both compete for the same prey. They are both predators competing for the same prey. So we give them the system. X represents one species, Y another one, and we ask them to analyze why the difference between the 2 systems. You notice there is a negative sign here, there is a positive sign here, there is a positive sign here, a negative sign here. So they go into this debate, into this discussion among themselves. Why is there is a negative sign here and a positive sign over there? What do those signs mean in terms of the population of these species? What is this term X times Y? What does it represent? What happens if one of the species does not exist? What happens to the other species? So all of these are discussions that take place amongst the groups. And then, of course, I go around and we discuss those, and then we present our findings. One group presents its findings to the entire class. And then we ask them to create their own model. At this time, we ask them to create a predator-prey model. So this one is a cooperative species model. This one is competing species model. Now I want predator-prey model. And fortunately, because of that detailed discussion of these 2 models, most students, most groups are successful in creating the model themselves. So they play around with the signs, because the signs are what is important in these models, to obtain a predator-prey example or model. So this was quite successful, I would say, in my classes. Another example that we do in these units, in one approach to finding a solution to a differential equation, we do something called the phase line. So in a traditional classroom, the phase line is this vertical line here that says P here. We just tell them, draw this vertical line. We tell them where to put arrows pointing upwards, where to put arrows pointing downwards. We tell them where to put those dots here, such as this black dot here. Of course, they all have meanings for the equation. And then we tell them how to do these things. Well, in an IODE curriculum, we don't tell them how to do these things. We want them to reinvent that line itself. So we give them a sequence of exercises that would actually lead them to reinvent that line. And those are two samples of what the students reinvented in my classroom, in my classes. In this example here, where is my arrow? I don't see my arrow. So the figure to the left, you see, where is my arrow? Oh, here it is. So this is the phase line that the students have actually created or reinvented. It was not vertical, it was horizontal, but so what? I mean, I could have done it vertical. So they have this horizontal line, they have these arrows to point something is increasing, these arrows to point that something is decreasing, similar to the arrows we want them to put here in the actual phase line, but they have them done differently. This is another example on the right also. This time the phase line was vertical, but the arrows are put in a different way. But the important thing is that, you know, they actually created this phase line. They created this phase line. And this is what is important. They reinvented that notion. Of course, at the end, I interfere to tell them that, you know, it is common to have this phase line vertically. I tell them exactly what is common in the mathematical community, what is considered correct in the mathematical community. So those are samples of the things that happened in my class. Let me share with you some of the results of surveys or questionnaires I give to my students. So I'll share with you some of the successes they feel that they were successes and some of their concerns as well. In terms of successes, they expressed satisfaction with the way the course was delivered. There were some students who were very critical, but eventually they grew to like the course and appreciate how it is being delivered. Many of them attributed the success of that experiment to the inquisitive nature of the units and how they are related to real life. And here are some of the comments that that they have written to me. Some of them are very interesting. We were able to ask freely if we are as if we are discussing our internal thoughts loudly. I learned that even in a mostly objective subject like math, listening to multiple people's opinions can really change the way you think and adapt to the course content. And one last is group work and deductive way to solve the course material help the student to understand. Now they had concerns, of course, because there were other sections taught differently. They were concerned whether they will be covering the same material. They didn't like very much the lack of textbook. Some of the open-ended questions in the units were very difficult, so they did not think they were very helpful sometimes. And at the end, some of them preferred that I would combine lecturing with inquiry-based delivery. So going back to facing the challenge of teaching versus learning, this experiment showed that actually they were learning, I was not just teaching them, but they were also learning the material. They were reinventing it. They felt they owned the concepts because they were reinventing them. So to face that challenge of learning, of teaching versus learning, there is a need, of course, for teachers to experience with innovative learning techniques, learning rather than teaching techniques. This need has created opportunities for mathematicians and math education researchers to collaborate together to explore innovative approaches to teaching and learning. So mathematicians and math education researchers are doing research together to explore innovative ways to learning mathematics. Many undergraduate mathematics instructors are now increasingly aware of the value of active learning, such as the case with inquiry-based instruction. Of course, with the online teaching now that we are experiencing, many are also experiencing with flipped learning techniques, which is another method of active learning, which was not perhaps something that was even considered in the past in a mathematics classroom. It is being now more and more used. And in my experience, this guided journey of learning in the IODE class benefits students in many, many aspects. I would like to end with just a list of some of the research I have conducted in my differential equations classes, the last of which is about this, exactly this experiment I was talking to you about just now. The title of that research is Inquiry-Oriented Differential Equations, a Guided Journey of Learning, and it was published in the Teaching Mathematics and Its Applications. I have also published before papers on the teaching and learning of differential equations. I have incorporated writing in my classes, in my differential equations classes, even in some abstract math classes, I ask them to write. I have incorporated visualization in my classes, all of these approaches to enhancing the learning rather than the teaching. I hope this was interesting to most of you, and thank you very much for listening. Thank you, Dr. Hinanati.
Thank you very much, Dr. Habre. I found it amazing, but you know, I love mathematics, so I thought this was amazing. And I also love talking about pedagogy, and I loved seeing how the students reacted to this different way. And I can see lots